Okay, so today's talk is going to be about image processing, and I'm sorry it's going to be quite fast. Forgive me. My name is Omer. I work at C. We have a booth outside. So before I begin, imagine that you are working on a video streaming app, okay? So you are working on this app, you are receiving images in real time. So you're receiving these big ass pixel buffers in real time, and you need to do some processing. In particular, you need to rotate them, maybe to match the device orientation or whatever. You just need to rotate them. Just think of a use case, okay? How fast can you do it? You have to do it fast enough so that you need to match 60 FPS video, let's say. So that means you need to do this operation within 16 milliseconds. How fast can you do it? So, in order to analyze this question, first thing we're going to look at is, what is an image? Well, quite simple. I mean, just take a close-up of your LCD screen. You'll see image is just an array of, it's just a 2D grid of pixels, right? And you can see in displays, they are usually represented by RGB values, or RGB and alpha values. You control the intensity of those values and you get all these kind of different colors. That's how displays work. So a good way to represent that in memory will be the RGBA, ARGB, BGRA color space. Take your pick. And the idea here is very, very simple. You have 8 bits for each color channel. So alpha, red, green, blue, and based on that, you can represent pretty much any other color. And this format is called ARGB 888 on Big Indian, BGRA on 888 Little Indian. Fun fact, iOS devices are Little Indian, so they will use the BGRA variant. So 1 pixel, this means that 1 pixel is 4 bytes, okay? Just keep that in mind, that's the important thing here. Each pixel is 4 bytes, okay? That means that a 720p image is going to be 3.1 megabytes. That is huge. If you want to do any operation on that, that is a lot of pixels to worry about. That's a lot of memory to worry about. Is there any way we can optimize this in terms of representation? Turns out there is. So we have this concept. This is a very famous thing called YCBCR. It's also called YUV, YPCBCR, YCC, etc. Basically, it's a color space. You can think of it as it's just applying some mathematical function on the RGB channels, and you get these new channels called Y and CBCR. They're also called Luma and Chroma channels, okay? So the basic idea here is that your Luma channel, you can think of it like a grayscale. It's just a grayscale, okay? And your CBCR are the other colors. Now the nice thing that we can do with this representation is this concept called chroma subsampling. Sounds complicated, I know, but the basic idea here is that as human beings, we suck at color, okay? Our eyes are really good at black and white, but we can't recognize colors that well. So here's a handy trick. Why don't I be sneaky and reduce the amount of color information in my video, okay? So I will put more black and white information, but less color information. And that's the whole idea behind chroma subsampling. What that means is, for a block, if I have a block of pixels, I will have 4 blocks of Luma pixel, but I will only have 2 blocks of chroma pixels. So if you're probably wondering why. Like, why should I do this? This makes no sense. I don't need to do this, right? Here's why. A square of 4 pixels in RGB will use 12 bytes because, 4 bytes, 4 plus 4 plus 4, etc. So if you use a YCBCR, you will use 6 bytes instead for just the color channel, and that's half. So you reduce your size by half just by changing the representation at no what you call meaningful loss of quality. Okay? So this is great. So let's go ahead with this. And fun fact, we don't need to do much. Turns out iOS loves YCBCR. So if you ever open CV pixel buffer format header, you'll see this super long name, super long enum there. And this is the default format for video. If you're ever using video and you get buffers from your camera, or if you're using replay kit and you get buffers from the screen, this is the format you'll get them in 420 YCBCR. Okay? The thing I want you to focus on here is the biplanar bit. Okay? This image is biplanar. I will explain what that means in a bit. Okay? So let's go back to rotation. Think about our rotation problem. Let's say you have an image, right? It looks like this. It's just a grid of pixels, right? And you want to rotate it by 90 degrees. It's a very simple problem. You have some point x, y. You just need to map that point and put it in its new location, which is something like that. It's just a very simple data movement, right? You just have this memory grid. Just need to move each pixel one by one and put it in the right place in the grid. That's all you need to do, nothing much. So What about the same thing for a YCBCR pixel buffer? It's the same concept. It's just that we have two planes now. We have a luma plane and a chroma plane. So the only difference between the RGBA case and a biplanar CBCR case is you just need to do it twice. Once for the luma plane and once for the chroma plane, because the luminance values are stored separately from the chrominance values. That's the meaning of biplanar, two planes. Okay? So, done that. Let's do this the most naive way possible. Okay? Let's write a loop and just do this. Okay? So we write a loop, we just iterate through the width and height, and we just assign go pixel by pixel and assign it to the correct position, right? Quite simple, very easy to do, can do it very fast, but don't do this please. This is very, very slow. You can imagine why. You are moving only 1 byte per loop iteration, and you have 720 times 1280 iterations for a 720p pixel, so it's a 720p image. This is going to be very, very slow. So let's search through the iOS libraries. Let's use GitHub. Let's use Stack Overflow and see if we can find any other better way to do it. And turns out there is. So good thing is these days most modern CPUs come with this thing called vector processors. So vector processors are this part of your CPU. They support what are called single instruction, multiple data instructions. Okay? What that means is one CPU instruction, instead of moving 1 byte at a time or 1 word at a time, you can move a vector of data at a time. Okay? So this is pretty good because you can make your algorithm a lot faster and a lot more power efficient because you are moving much larger chunks of data much quicker. And the nicest part about Accelerate is Accelerate has several functions optimized to use this vector processor. So they have met functions for image processing, signal processing, etc. And if you want to look at the code, it looks something like this. You have this method vimage rotate. You just call it. You pass it some pixels, pixel buffers. It will handle the rest. Okay. Just need to keep in mind that you need to lock this thing. Okay. This can work really well. We're good with this, but there are some problems. Vimage is super fast, but the processing is still on CPU. So if you're CPU bound and you can't spare any cycles at all, let's say you are doing audio processing or something else. While in this app, you don't want to spare a single CPU cycle for doing this stupid operation. This may not be ideal. And there are some synchronization problems with vimage as well. In iOS, GPU and CPUs share memory. Okay? What that means is the GPU and CPU can access the same memory address actually at the same time. And there's no built-in synchronization for this thing. So the reason for this is great because this is pretty good for performance. This means when you copy stuff over from GPU to CPU, you don't need to copy anything. It's the same thing. There's no data copying needed. But this also means that you are responsible for synchronization. And if you're working, and there are some examples where this can be a problem. So attempt 3, yay, let's go deeper and let's just use GPU to do this directly, okay? So, talk about over-engineering. What we're going to use instead is we're going to use Metal to do this. So iOS has this beautiful low-level API and programming language called Metal where you can program your GPU directly. And the idea is to utilize the massively parallel nature of the GPU for this problem. Okay, because we're going to pixel by pixel, we can parallelize this problem quite easily. So just a quick intro to those of you who are not familiar about CPU and GPU. A CPU, you can think of it as having small number of cores that are very, very powerful, that can do a lot of optimized for a lot of different kind of control flow. They have all these branch prediction and all this complex stuff. A GPU, on the other hand, has hundreds of cores, but they are very simple. So they are optimized for doing massively parallel problems that you would want to do you want to spread over. It's great for graphics processing, basically. Okay, I can't obviously talk about the Metal pipeline in 10 minutes, but if I was to do it in one slide, this is what it would look like. Your CPU program will basically feed your what's called a vertex shader with some vertex data, which the GPU will render into some primitives, and those primitives will be rasterized, and then they'll be converted into fragments where you are allowed to color the fragments, basically. So the point is, in the GPU, right, you only have 2 places where you can control the GPU. One is this thing called a vertex shader, the other is this thing called a fragment shader, okay? And if you think about it, you need to connect these 2 worlds. You need to connect the world of GPUs to the world of core video and CPU pixel buffers. So how do you do this? Actually, there's a very simple, iOS provides us a way to do this. Core video has this very nice thing that allows you to create textures from images. So there's this CV metal texture thingy, which lets you create a texture out of an image. And this is how you can create a metal texture from your pixel buffer, and then you can send it to metal, and you can write your vertex and fragment shaders to do the rest. So like a quick idea of how what that would look like is, I won't go through this in too much detail. Basically, you can write vertex shaders, and shaders look something like this. I'll just show you what they look like for fun. I don't have time to go through this, but the code is quite simple. Basically, this is all your fragment shader will look like, and this is great. It's complicated to set up though, because if you if you do graphics programming ever, if you've seen the hello triangle, which is the hello world for graphics programming, it is damn complicated to set up this thing. And you need to embark on this super fun learning curve to picking up metal, but it's good, it's worth it. The problem with this is that because, like I mentioned, iOS does not handle CPU and GPU synchronization, you have to manage it yourself. So you have to do things like triple buffering, which basically means you have to do something like this. You have to, the CPU has to constantly keep sending frames, and at the same time the GPU is going to read from the frames and process them, so on and so forth, in a pipeline way. Okay? So, I mean, that's it. This was a lightning talk.
Great. Yes, yeah. Very fast. Thank you, Omer.